Okay, this is problem number 36 from your textbook. It describes a 5 kilogram block that moves in a straight line along a horizontal frictionless surface under the influence of a force that varies with position, as shown in a figure which I have recreated for you on this page. The scale of the figure's vertical axis is set by F sub s as equal to 10 newtons. So this F sub s is equal to 10.0 newtons. And this is describing a block. It doesn't provide a picture, but I'm just going to draw a little picture real quick about a 5 kilogram block that is moving on a frictionless surface under this particular force. And this shows the position in meters and our particular force. So let's see, the question is how much work is done by the force as the block moves from the origin to x equal to 8.0 meters. So the question is how much work is done by this particular force. And it seems like a fairly reasonable problem. I mean, something that you might do initially is write down something like, well, the work, I know that the work is equal to whatever the force is times the displacement, right? The scalar product of the force and the displacement. One problem with this is that this is true if the force is a constant force, but we obviously have a force here that's variable, and the question asks us for the amount of work done from 0 meters out to 8 meters. I should put a little 0 here. From 0 meters out to 8 meters. And the force obviously changes over that time. So this is not all that different from some of the problems that we've done in class previously, where we're asked to kind of construct this a little bit more piecewise, to look at what the total work is done. And so what we're going to look for the net work the work done by this particular force, is we're actually going to end up summing up over the pieces of all the little bits, right? So the work done from 0 to 2 meters, which describes the force at this point, and then we're going to add to that the work done from 2 to 4 meters, and then from 4 to 6 meters, the work done from 4 to 6 meters, plus the work done from 6 to 8 meters. Right? Each of those little bits is going to contribute somewhat to the force, and some of those quantities might be negative, right? Some of these, here we have a force that's listed as a negative quantity, and so we might see that as being a real issue. So given the fact, just a little bit more about this graph I think that's important, is that it tells us that F sub s is 10 newtons, and that the 0 quantity is here, negative F sub s is down here, which means that each of these points here in between, this would be negative 5.0 newtons, and this would be positive 5.0 newtons in between, and that might be particularly useful. So as I've kind of split this up already into the pieces of the work that I need to be able to consider, each of those is going to be important. It's pretty obvious for this first piece, at least I believe it's pretty obvious, that the work done is going to be equal to that force, the force done between that interval, 0 to 2, times that displacement, which is just a displacement of 2 meters. And this is moving, it says it moves in a straight line, and these forces are all in a straight line, so we don't have to worry too much about the scalar products. I'm still going to write a dot here just to be, because I like using the dot for multiply, but we're going to be multiplying by 2 meters in that case, and then in each of the successive instances we're going to be multiplying the force acting between meters 2 and 4 times its displacement, which is not 4 meters, right? It's just 4 minus 2, so 2 meters. Plus the force between 4 and 6 times 2 meters, plus the force between 6 and 8 times 2 meters. And we need to make sure we have the correct value of the forces in each of these situations. All right, so for the first instance here from 0 to 2, we have a constant force, and we actually are told what that is. It's F sub s. And I could plug in 10 newtons if I wanted to at this point. I'm just going to leave it as F sub s, because I think it's a nice generic value. So times 2 meters, plus the force between 2 and 4 meters, which it seems like it's changing. So you might feel, oh, well, it's not a constant value anymore. We need to be able to integrate it. And we probably could define what the function is during this point, and then do an actual integration of that function. But it's kind of a lot of heavy lifting, considering the fact that we can look at this geometrically and say, well, between 2 and 4 meters, it's decreasing linearly. We know exactly how much it decreases over that distance, and so we can tell that the average value is going to kind of be the mean value between these two quantities. And that would give us an average value of 5 newtons. So the average force between these 2 points is what we're really interested in, and that value would be 5 newtons. So we could simply take F sub s divided by 2 here, multiplied by 2 meters, plus between meters 4 and 6, we have a value of 0, right? This is a 0 Newton force. So we'll just plug that in as 0 newtons times 2 meters. plus the force between 6 and 8, which this is again decreasing, but this is still an average value that would be something like the F sub s divided by 4, right? It's a mean between, it's the average value of the force between meters 6 and 8 that would be about equal to this F sub s divided by 4, half of that. But also negative, right? This may be decreasing, and this is something that maybe I think a lot of students got caught up on one of the questions for, if it wasn't the last homework assignment for homework number 5, it was probably homework number 4, where people thought, oh, well, this is decreasing, therefore it must be a negative quantity. And the average value of this is still positive, whereas the average value of this happens to be negative, right? Because it happens to fall below the 0 point of force. So that is going to be a negative quantity. So the force here is negative F sub s divided by 4, or 2.5 newtons, times 2 meters. Now we can go ahead and plug in quantities for each of these. This would be 10.0 newtons times 2 meters, plus 5.0 newtons times 2 meters, plus 0 newtons times 2 meters, minus 2.5, oops, sorry about that, 2.5 newtons times 2 meters. And we can kind of pretty quickly add all these up, right? This first quantity is going to be 20 newton meters. This is going to be plus 10 newton meters. This is going to be 0, so we don't need to worry about it anymore. And 2 times 2.5 gives us a negative 5 newton meters, which leaves us with a sum of 20 plus 10 minus 5 of 25 newton meters, right? So that's the work done by this force due to this kind of variable, due to this variable force that kind of changes. So we just added that up piecewise, and we get a really nice solution. Notice I kept the units in the entire time, so I was able to clearly determine here we have Newton meters, which, for answering a question about work, you're probably going to want to convert this into joules, which there's no real conversion, right? Newton meters is joules. But simply writing it as joules kind of reaffirms the fact that this is an energy quantity, which is what we wanted.